So we should have finished quizzes 9.2 and 9.3. If you haven't, remember you can take them anytime, redo them as many times as you want. We had a little bit of issue with the lab titration last time because we had kids that needed to leave for the college tour. We will have a little bit of time depending on how well you prepared you are for the lab next time. You might be able to finish it next time. Also during tutorial today, I'm opening it up. I'll be back there. I'll instruct you again step by step how to do the quick titration and the longer titration. Okay, so if you're interested in doing that, you can do that and be on top of it. Remember, I won't be here Monday, so tutorial Monday you can come, but you can't do any work there. I will be here Tuesday, which is your guys' day, and we'll do the lab on titration of buffers. We're going to be doing grape juice, pineapple juice, and apple juice, I believe, that you're going to titrate and see how they titrate. You're also going to be testing different indicators and what color they are in different pHs. So make sure you look over that lab. In fact, let's bring that up just for a second so we can talk about it. So we're going to be doing these acids, and they're in apple juice and grape juice and tartaric acid. How many have mothers that can grape juice? Okay, have you ever noticed down at the bottom of the grape juice there's like crystals sometimes? Those are tartaric acid crystals. And that's what we're going to be testing it for as tartaric acid. Citric acid, you guys basically know, is vitamin C, and then malic acid is found in apples. So we're going to be testing each of those. I've sort of set up the longer or the nicer version of this. You'll still want to do a quick titration, a quick look at where it's going to change so that you know where to slow down. So when you do your long titration, that you're not spending a lot of time, okay? So you're going to be doing 6 titrations next time. Now, if you've got it down, it's not a big deal. If you don't have it down, then it's a big deal. When you do your pH probe titration and you actually get the graph, you actually have to come and download it before you do your next titration. But one person can be downloading and the other one can be doing the quick titration of the other one to see where you need to slow down and setting it up again so the next person comes back and you do it again. So use your time wisely. You're going to need to have a computer up again, and I will run you through one again back there so that you'll have an idea, because we really didn't get to run through like the other classes got to run through 2 quick, easy titrations, seeing where the things were, and then a longer titration, seeing where the other thing was. Okay, so but on this one, you've got a pre-lab that doesn't need to get done, so you need to do that beforehand. It sort of shows you the titration curve that you should be getting, safety precautions, procedure. This procedure right here is where you're going to be testing the indicators. You're going to have test tubes that you test the indicator in for each of them. You'll have a table here where you're going to tell me what test tube it was, what was the name of the indicator, what was the initial color, final color, and I'll be giving each of you a different one so that you can talk to other people and see what kind of indicator they used and how did it change. You'll notice the procedure here for B, the titration, is open and blank because I want you to tell me how to do it. Okay, so that we really need to go through the first one so you can know how to do this. You want to do a quick dump titration, and we talked about how to do that with the flasks, and then you want to do a slower titration with the pH curve. So again, if you come during tutorial today, that will help that. You'll have procedure B, things that maybe you need to set up, like how much juice are you going to measure out, a place for beginning, burette, end burette, so you could do a quick test of where you need to slow down. Then you've got your analyzing the results, and you'll need to attach the 3 graphs that you make. Okay, so that's a lab for next time. So make sure you're prepared for that. I will give you next time the buffer lab, and we're going to do a buffer lab. That one you do just once. There's going to be a quick dump, and then you're going to do a fancy one after that. So if for some reason you get off here, you'll have a little bit of time on the buffer lab that you can use in class. But lab notebooks are due that day, so you need to be ready. Remember, you've got your pH lab that you're doing at home. That needs to be included. So we'll have 4 labs coming in. Okay? All right, so we're going to do lecture right now, so if you'll go real quick, we got to catch up. The other classes are ahead of us, so we're going to do a quick lecture. Yes?
I'm going to have to turn in my lab notebook on the 14th because I won't turn on the 15th.
So the 15th is a buffer lab, so you'll miss a lab. So you either need to come in today after school and do the lab, or you need to come in Tuesday before school to do the lab.
I might be there now that I'm thinking that because the band leaves for tour on that day, but I think we leave at noon, so
Okay.
I'll probably be there.
So, okay. All right, let's go through these really quickly. Reacting all of the hydrogens, write the molecular equations of the neutralization reactions of the following. So we just need to be able to write the equations. I believe this is where we left off. Is this true? Okay, so lithium. Lithium is Cal 1. It's a +1, so Li. Hydroxide is OH. It's a -1, so LiOH. Plus acetic acid is actually H. Let's try that again. HC2H3O2. That's just hydrogen with the acetate ion. And when we do a neutralization reaction, it's OI. Outsides go together, insides go together. We've done this before. Li is going to go with acetate. They're +1, -1, so they just go together. And H and OH will go together, making water. And since they all have one plus or one minus charge, it's already balanced. If we look at the next one, sodium hydroxide, sodium is Na, hydroxide is OH, +1, -1, they're already balanced. Plus phosphoric acid is phosphate with hydrogen. Phosphate has a -3 charge, so that means I need 3 hydrogens with it. Since they want us to react all of the hydrogens, we're still going to do OI. So outsides and insides. So sodium, which is a +1, will go with a phosphate, which is a -3. So we need 3 sodiums with the phosphate. And the H will go with the OH. H is a +1, OH is a -1. We make water, but this is not balanced because we have the phosphate that has a -3 charge. So we need to quickly balance it. So we need 3 sodiums because we've got 3 sodiums in the product. We put a 3 here. Now we have 1 phosphate, but we've got 1 oxygen, and we have another 3 oxygens here that are not attached to the phosphate. So I'm going to put a 3 in front of that, and then my hydrogen's 6 and 6. So we're balanced. Okay, last one. Barium hydroxide. Barium is a +2 charge. That means I need 2 hydroxides to go with it. Plus hydrochloric acid is HCl. Plus a hydrogen is a plus and a chlorine is a minus. Again, OI, outsides go together and insides go together. So barium is a +2, chlorine is a -1, BaCl2, plus the insides go together, H and OH make water. This is not balanced. I can see really quickly I have 2 chlorines on this side, I only have 1 on this side. So I'm going to put 2. Barium's okay. Oxygens and hydrogens are not okay. I have 4 hydrogens on the reactant side, so I need 4 hydrogens on the product side, and that takes care of my oxygens also. So this is just balancing equations like we've been doing, okay, for forever. So not a big deal. This is a neutralization reaction, though, because each of these have a water and a salt. That's what we call it. So when you end up with a water and a salt, it's a neutralization reaction. Which of the 3 types of theories are we looking at here? Remember, there was Arrhenius, Bronsted-Lowry, and Lewis. Which one is this? Middle of the bullseye. This one is Arrhenius. Remember, Bronsted-Lowry, we're going to end up with charges, ions. And Lewis, we're going to end up with one thing in the product. So those are the way you can tell back and forth. Okay, so here we have a titration that's going forward. We've got 25 milliliters of HCl that required 45.92 of 4.3 molar KOH. So the easiest way to do this, I'm going to do up here real quick, is just using the equation Ma. Is that easier to see or is this easier to see? It's just bad either way, right? How about black? Ooh. Let's try that again. Whoops, forward, forward, forward. If I use black, is that better? I know, this is not good. I needed to put white behind this. But if I use the equation MAVA equals MBVB, this is the same one, M1V1 equals M2V2, or C1V1 equals C2V2, as long as the relationship is a 1-to-1, meaning one hydroxide to one hydrogen. As long as that's true, I can do this. I can just throw in what I need. So I'm trying to find the concentration of the HCl. So I just rearrange this, Ma equals MbVb divided by Va. And I'd plug in, and I'd get my answers. As long as it's 1-to-1, I can do that. If it's not 1-to-1, if I have two hydroxides to one hydrogen, then I've got to find the moles, go to the equation, mole to mole, and then take that mole and divide it by the volume again. Okay, so that's the way that I did the rest of this. So I would take the molarity, change it to moles. Then I have to write a balanced equation. Since it's all 1-to-1, I don't have to use that. I can use the MAVA, but if not, then I'd have to go moles to moles. Okay, going forward, I'd convert moles to moles. So this right here would not be 1-to-1. Since it's 1-to-1, I can use that MAVA. Okay, now, then I take the moles of hydrogen and divide it by the volume, and I finally end up with the molarity of the acid. That's how I have to do it if it's not 1-to-1. If it's 1-to-1, I can use that MAVA equals MBVV, okay? All right, so going forward. Here we have how many milliliters. So I'm looking for a volume. Here's my concentration, and they've got this and this. So I can really quickly use that MAVA equals MBVB, plugging through. I am looking for my volume of my base, right? So solving for that, volume of the base equals MAVA divided by MB, plugging in what I have. I've got 15 milliliters times 0.10 molar divided by 0.15 molar. If I've done this right, the units should cancel and give me a volume, which they do. Plugging it through, 15 times 0.1 is 1.5, divided by 0.15 gives me 10, right? Milliliters. And that would be of the NaOH. Everybody okay with that? I know I'm going a little bit fast, but it's just plugging in. So you've just got to identify which is your acid, which is your base. Make sure you keep the units of each of them together. Okay? Yes, ma'am. Right here. 1 OH to 1 H. So if it has an H2, or if it has OH in parentheses with a 2, then I've got to find moles first, then use the balanced equation, then go back to molarity. Okay, yes. Good question. So if it's not 1-to-1, then instead of this being equal, I would have to find MBVB, find out that, which is moles, then write an equation to balance it. Then I would go moles of that to moles of whatever I needed, which, so this is moles of base. I'd need to find the moles of acid. Once I found moles of acid, then I would divide it by the volume, and that would give me molarity of the acid. But since this right here is 1-to-1 in this one we're doing, we can skip that stage and just put it equal to each other. Okay? Good questions. We okay to go forward? All right. So let's do another one. I want you to take a second and see if you can do this by yourself. I'll put it up here in just a minute, but go ahead and try. This is an unknown acid. We're going to assume it's H and just one H, so 1-to-1. So go ahead and use MAVA equals MBVB because we can't do anything about it anyway, going mole to mole because we don't have an equation. Oh, sorry, we're just setting it up. Oh, tell me how to set it up. Sorry, I just read the whole thing. Explain how to set up a titration using a 0.1 molar NaOH and 10 milliliters unknown acid. So this is what we were doing in the back last time, but we got sort of messed up. So here's our titration, burette tube. Okay, I'm a very visual person, so when I go to describe stuff, I draw pictures. So first get my burette. I'm going to add into here 0.10 molar NaOH. That's my first step. So I'm actually going to prime it with this and then fill. Okay? So that's actually 2. All right, then we have our beaker down here, or a flask. It doesn't matter what you do. You're going to add, for the third step, 10.0 milliliters of acid. And fourth, I'm also going to add indicator. And this one, I'm just going to do a quick, fast titration, right? Because I want to do the quick, fast titration first. If not, then I could set it up with a pH meter. But I'm just going to show them how to do the fast one. So I'm going to add an indicator. Then, for the fifth step, I'm going to add, drop by drop, the NaOH till indicator change. And I'm going to record volume. And MAVA equals MBVB to find out the, I probably should put the 0.00 milliliter level. And I'm done. That's the basic titration. So if as I'm doing a fast titration, this is the one I want to use. I want to find about how much it is. It's not going to be as exact as we do it with a pH probe, but it will give me an idea of where to slow down. Okay? So we're always going to do that. All right, let's go ahead and go forward. We have to talk about acid rain. This is part of the core as far as the state goes. When we talk about sulfates, sulfates mixing with water will give you sulfuric acid. And I don't know if I put this down on this because you guys have had acid rain from 7th grade on. So I just assumed if you need to write it down, do it. Nitrates are another thing that we consider acid rain. So nitrates are released. These are the ones that you can see that sort of have a brown look in the sky. Nitrates will have brown color to them. And when they mix with water, we get nitric acid. And then the one everybody's up in arms about is carbon dioxide making carbonic acid. Well, guess what? Carbonic acid really quickly decomposes back into carbon dioxide and water. Our Earth is made to use that. The only problem is we're putting more carbon dioxide in by using our cars and our vehicles and that, so we're saturating with carbon dioxide, and we're cutting down trees, which uses carbon dioxide to do photosynthesis to make sugar, blah, 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 blah. Anyway, so that's a big global warming kind of thing going on here with this one. So there's pros and cons to that. Yes, the Earth is warming. It has warmed a couple of degrees up because of this. But if we plant more trees and we plant more things like that, it'll take care of that as long as we don't keep clearing out to build houses. So we need to balance that. All right, so learning check. This is the one I want you to do on your own if you can. Just grab a blank piece of paper or a section that you can use to write this one and see if you can figure this one out by yourself. Now, I've put up there M1V1 equals M2V2, but it can be MAVA equals MBVB. So just find a place that you can use to write on maybe some notes that you've already done. On the pages or on a piece of paper. I want you to try and see if you can do it by yourself. It shouldn't be that hard. We're going to be doing this all the time with the titrations we're doing to figure out the molarity of an unknown, like in our apple juice or whatever. You what? Okay. Yeah, the calculators are in the sink if you need them. Okay, I'll give you about another 30 seconds, so we're going to come back together, see if you can get it solved by then. Shouldn't be a very hard one to solve. Okay, let's go through it. So basically, you would set it up. You're solving for V1 or VA. You plug in the things that go together, or VB, sorry. Plug in the things that go together, which are the 400 and the 0.1. Divide it by what doesn't belong, and you end up with 3.3 milliliters that you would need of your hydrochloric acid. So this one is a dilution equation, but it's the same thing that we'd be doing in titration. Okay, so we would put 3.3 milliliters of the 12.1 acetic acid in a 400 milliliter container that's filled with about 370 milliliters of water, because we need to put acid into water all the time or it splashes back at us. Okay, so that takes us to where we were supposed to be for last time. We're going to go into this. Don't forget to be working on your pre-lab or your home lab, and we're going to go into the next part of the notes. Okay, so water can self-ionize. So in any, even distilled water, you're going to have hydronium ions and hydroxide ions. But the thing is, they're equal amounts, so they neutralize each other. So we get the same amount. What type of reaction is this? What theory does this fall under? Lewis, Bronsted-Lowry, or Arrhenius? The one with the two names, Bronsted-Lowry. Yes, because Bronsted-Lowry has a positive and negative. So you think two names, positive and negative. Now remember, on the test, she's just going to call it Bronsted. But it is Bronsted-Lowry in most all other texts. So water will self-ionize. We get the hydronium ion, the hydroxide ion. The hydronium ion in distilled water is 10.-7 molar, and the hydroxide ion is also 10 to the minus 7 molar. So when we do the KW, yes? So neutral is when we have the same amount of both the hydroxide and the hydrogen ion. So this should be back to where we cut and went back to the titration. So we should be back at the first part. Keep going, keep going, keep going. So we should be right here and coming into the self-ionization. Neutral is 7. So it's the same amount of hydroxide and hydronium ions. And this is a yeah. I usually do, but this one I had to flip up because of me leaving. So we usually would go in order, but we had some issues. That top equation is a Bronsted-Lowry of the self-ionization of water, which is on the bottom of your page there that you need to write. So this right here is the self-ionization of water. Write the equation for the Lewis dot. We'll get there. Okay, so check the next page real quick for me. Write the equation for, so this right here is the equation for the product KW of water. So that goes at the very top of your page there. And we'll go back to the, if we don't get to the self-ionization of water in Lewis dot, at least put this one down and I can show you that later. Okay, so I'll give you a second to write that down. For H3O plus, yep. It's a charge. So in fact, I'm going to go back a slide and I'll come back to this slide. Let's go ahead and write the, this was actually the Lewis dot right here. This was a Lewis dot for that self-ionization of water. Water can be the acid or the base. Because it can be acid or base, it becomes what we call amphoteric. Amphoteric means it depends on who it's with, how it acts. So if it's with this group, it acts like an acid. If it's with this group, other group, it acts as a base. By what happens from one side to another. So if it's an acid over here, it's got to be a base over here. Right. So this acid donates a hydrogen to this one, and that's what you get on the other side. That's why you sort of see the red hydrogen in there. Okay. All right, so I'm going to go back here. Did you get this equation right here? Okay, did everybody get this bottom equation? The KW. That's the top of the next page. Okay, we ready to go on? All right, so we need to be able to do some examples. If you don't have a calculator, you're going to need one for this. So we're going to use that equation on the bottom of the page there. You need one? Anyone else need one while I'm grabbing? Pass them back. Whoops, sorry. Anyone else need one? Okay, so all you're doing on this is the equation, remember, is Kw equals the concentration of H3O plus times the concentration of OH minus, which equals 10 to the minus 7. So guess what you do if you want to find the one and you don't have the other one? You just take 10 to the minus 7, divide it by what you're given, and that'll give you your other one. So this would be concentration of H3O plus would equal 10 to the minus 7 divided by 1.0 times 10 to the minus 7 in parentheses, which would be 1, right? And we usually do that, we'd go 10 to the 0 molar. But when it's just 10 to the 0, you can knock that out because that's just 1. So let's do this next one. We would go 3.8, whoops, try it again. 10 to the minus 7 divided by parentheses 3.8 times 10 to the minus 2, close parentheses. What do you get for this one? Your calculator? Do you need a calculator? 2.6 times 10 to the negative 6 molar, and that would equal my hydronium concentration. Okay, go ahead and do the next 3 or 4. Again, you're just going to take 10 to the minus 7, divide it by, put whatever they gave you in parentheses, and you'll get your answer. I'm going to pull some of you to go ahead and write these up here, so make sure you're doing them. Give you a few minutes to get it going. So you put 10 to the minus 7 in and divide it by parenthesis, whatever number's up there, close the parenthesis, you got your answer. Yeah.
So this doesn't have like a 10 to the
That should have a 10 to the negative. Okay, yeah, it would have been 10 to the plus 1, so you're fine. Yep, yep. Yes. Okay. All right, that's fine. Okay, let's do. Brandy, will you put up number 3? Melanie, Nani, would you put up number 4? Princess, will you put up number 5? And Laura, will you put up number 6? So as soon as you get it completed, go ahead and put it up. You can check with your neighbors to make sure that's the right answer before you come up if you want to. Yeah. So you've got two significant figures on all these, so just give me two. Okay, there's a little button that is, the caret is this X with a box right here.
And the number 5 is 1.2, 10 to the negative 7.
So 10 to the negative 7 divided by 1.2, yep. No, if it comes out with like 10 point whatever, that's fine. Yes?
What if it has like nothing, like there's no 10 to anything?
So that would have been 10 to the minus 2, but that's okay. You can write it like that, 0.012. That's fine. Guys, remember, if it's bigger than 1,000 or less than 1,000th, we need to put in scientific notation. But if it isn't, we can just write the number. Why are we putting 0? You don't have to. You could have written this just as 10.5 molar. That's fine. 10 to the 0 is 1, so you're timesing it by 1.
It was 1.75, would I round it?
That's fine. That's fine. Oh, you're fine. Your coat just caught it. Okay. Okay, are we checking them okay? Has everybody got 3? What's up there? 10.5? Did you get that? How about number 4? 1.8 times 10 to the minus 4. We okay? You just have to get used to not touching the board other than where you're pointing, otherwise it goes forward. That's still okay, but you didn't go down to 2 sig figs. So if it gave you 2, you should report 2. Okay, so does anybody have any problems with anyone that is up here? Did everybody get those? So you're just taking 10 to the minus 7 and dividing it by what you're given. Not too hard, right? Okay, so going forward, we can do the same thing with finding OH minus. So this would just be the same thing going on here. We would go 10 to the minus 7 divided by 0.0035, and we would get our answer. Why don't you go ahead and do that? I'm going to pull some other people up to put this on the board. I've set this one up, but I have not calculated it, so somebody still gets to do that one. Give you a few minutes of sweating it before I tell you who's putting it up. Okay, got 4. Hayden, will you put up number 1? Emma, will you put up number 2? Ryan, will you put up number 3? And Ashley, number 4. Yeah, you'll need to round to 2 significant figures again.
Oh, so I can't do 1.5 to 1.2.
One more time, what?
1.15
1.2, yep. 2.9, just 2.9. Now, quit being snarky. I don't think I called you, did I? Okay, raise your hand. Number 2, who has number 2? Okay, Ryan has 3 and Ashley has 4. Sorry, not Ryan, Ryan. I'll try and put the emphasis on the right syllable. Ryan. Syllables. That's the only way I can keep Ryan and Ryan separate.
Just write that 0.001.
0.0010. No dying allowed.
That's about it.
It's like Lysol. Oh man, after she left, I was like, oh my gosh, ooh, I don't want anybody catching that.
It comes back here, it just like downs the whole table in the back there.
Because there was a girl that left because she'd been throwing up, but she came to tutorial and signed in. And so I was like, oh, I do not need that. So after she left, I Lysoled everything with kids around. It's okay. No. Do we have any issues with the answers that are up here? Everybody able to get them? Okay, pretty easy, right? Choose one. 1.15, they rounded up. That's what they got, 1.15. Okay, yes. The scientific notation would be 1.0 times 10 to the minus 3. You can use it or not use it. Usually if it's bigger than 1,000 or less than 1,000th, we do. Okay, so let's go forward. pH scale. This is what you need for your home lab. Okay? Now, depending on how far we get today, depends on what brings in the lab. We'll definitely have the 3 labs coming in, which is a titration, the pH home lab, and our beverage titration. If we don't get to buffers, I'll push that one off to the next hand in. Okay, so pH, basically that's our way to quickly do a scale that's very simple. So it goes from 0 to 14, but guess what? You can have negative and you can have greater than 14 if they're really, really strong acids or really, really strong bases. So you can get negatives and you can get above 14. But for the basic area, we use 0 to 14. Okay? 7 is considered neutral. Anything below 7, 6.9 and below is considered acidic. Anything 7.01 or above is basic, yes.
What would be like an acid that goes below
12 molar hydrochloric acid, 18 molar sulfuric acid. Really strong. Yeah, really strong. Okay? All right, so again, greater than 7 are basic, less than 7 are acidic, right at 7 is neutral. You'll need to, if it's a solid, you'll have to dissolve it in some water and then put it on. It's solid on the pH paper won't work. Okay? All right, so just to give you some ideas, and you should be testing this at home. Remember, you have to test 20. So battery acid is a 1, lemon juice is a 2, vinegar is a 3. Adult fish die between 3 and 4 if we get acid rain and stuff going on there. If we have between 4 and 5 in our waterways, then the reproduction of fish changes. Normal range of pH of rain is between 5 and 6. Why would you think that? Because 7 is actually neutral, and as it's falling through, it's catching particulates, and it's catching any carbon dioxide, nitrous oxide, or sulfur dioxide that's in the air, so you get a little bit of an acid. Yes?
Okay, so I did a few of them for lab, and I got 6 for vinegar. Like, I don't think...
So it depends on your concentration. It depends on your concentration. So depending on the concentration of your vinegar, there are different concentrations. So you're okay if you got 6. It's still acid, right? If you got an 8, then I'd be concerned. Okay? So as we look at the basic side, we've got baking soda, seawater, milk and magnesia or Tums, ammonia, and lye, which is sodium hydroxide. So going forward, here's some more that you can just look at and see, get some ideas of things that you can test. If you test liquid plumber or something that's like Lie that's up here in the basic section, you need to get that recorded really fast, because what happens if you use bleach, it'll actually do blue and then go white because it's bleach. So you have to get that color really quickly. So this gives you some ideas. So equations that we need for the lab. We have this one already. We've been using it. But we've got this one. Now we're going to use a log function. So that's so that it makes it an easier number to work with. So pH is equal to minus the log of your concentration of hydrogen. pOH is minus the log of the concentration of hydroxide. pH plus pOH equals 14. If I want to find the concentration of hydrogen or hydroxide, I go 10 to the minus pOH. If I want to find the concentration of hydrogen, you do that. Now, here guys, before you all take pictures, I actually have a handout for you. I'll pick up the extras on the other side. Now, you'll notice that pH and pOH, all you have to remember is when there's a P, it's minus the log. P just means minus the log. Minus the log of whatever you're looking for, H or OH. Okay? If I'm trying to find the concentration, then I just go 10 to the minus pH or pOH, whatever I'm trying to look for. If I remember they add together equal 14, I can go back and forth between any of them. Okay? This little square, which I've got on the next page, will help you. Now, if you want to remember that bases are blue and acids are red, you can color it however you want. But this is yours to keep. And it'll help you remember what to do. So if I'm here, I can go straight over to H+, or I can go up to pOH and go across. Okay? Okay? All right, so let's try this. So I have a pH of 7. Is it an acid, is it a base, or is it neutral? So we're just doing basic stuff right now. It's neutral, good. So I'm just going to put N. Is pH of 3.5 what? Okay, pH of 4.5. pH of 14. Okay, really fast, really easy, right? Now, if it would have been 10 to the whatever, I have to think about it a little bit more. But as a pH or pOH, I can do really fast. Okay, when we calculate, remember the brackets mean molarity, so it has to be in molarity. You can't do moles, you can't do liters, you have to make molarity before you plug it in. So, going forward here, if I have a hydrogen concentration of 10 to the minus 10, then if I do minus the log of 10 to the minus 10, what do I get? Plug it through your calculator. Now, 1 times 10 to the minus 10 is still 10 to the minus 10, right? So do I have to put 1 times 10 to the minus 10 in my calculator? No, I can do minus the log of 10 to the minus 10. Done. Okay, what is it? 10. Guess what? It's just the exponent as long as this number's a 1. Okay, so I can do that really fast, right? I can just look at it and not even put it in my calculator. Now, let's do another one. This one is not 1. So this one I have to put in. I have to figure out minus the log of 1.8 times 10 to the minus 5. What is it? Log is just a button on your calculator.
No, but then I'm doing it in math. It's just not there.
All you have to do in here is push the log button and plug it in. 1.7? Did we get 1.7 or do we get something else? 4.7. It should be close to this one, a little bit above or below. If you get something way off, you know you're off. You try it again. Okay, so that's a little trick to help you do a double check, okay, on your answers. Nope, the next part is, I just did some example right here for you. Now, yeah, you're going to be using it. So we're just going to work through some problems, and then you actually have some practice ones here on your thing. So if I have a pH of 4.5, I can ask you to find hydroxide, hydrogen, hydronium, and pOH. All I have to do is use that square. So where am I on that square if I have a pH? Upper left-hand corner. Good. So I can go down or I can go across and down. So easiest way subtract that from 14, I've got 9.5, right? That's my POH. So I just went across the top to get POH. Now I need to get the hydronium and hydroxide ion. Here's my exponents. So I would say that my hydronium ion is just 10 to the minus 4.5. I cannot leave it that way. I've got to put it through my calculator. And this is the concentration. Okay, I can't just report it as 10 to the minus 4.5. That's wrong. Okay, I can do the same thing with the hydroxide using the 9.5. Again, I should have molar. That's an M at the end that didn't work. Okay, 10 to the minus 9.5. Get an answer. Don't just leave it 10 to the minus 9.5. Okay? All right, so let's do this one really quick. This time, where am I? OH. Where's OH on my block? Bottom right-hand corner. So I need to find all of these again. What's the easiest way to do? What should I do first? So you go 10 to the minus 7 divided by that, or I could go minus the log of that, and I get POH. Doesn't matter which way. I like to go up around the top rather than down the bottom because I always forget to put parentheses around the bottom. Does that make sense? So I screw up. I know I do that. So I go around the top. Okay? So first thing I would do is go minus the log of that, and I get the POH. Then how do I get pH? Good. I subtract that number from 14. So I'm just following that pathway around. And then how do I get concentration of hydrogen? 10 to the minus pH. Plug it through my calculator. Okay? We all right? Okay, so this is pH of 6.73 is barely an acid. It's almost neutral. So we would put that. Okay, now I believe these are in your notes. I want you to try. I want you to find the pH. So I'm asking you for only one thing, but I'm giving you anywhere on that box. So do what you need to find pH for each of these. I'm going to have somebody come up on each of these and show how you did it. The log on there is, good question, right there.
So LN.
On this calculator, it looks like it.
Because we typed it in, it said LN, but LN I feel like it's different than log.
It is. It's base C. So you have to hit it twice. So if you're using my calculator, the LN and log button, you have to hit twice to get to LOG. So remember, you want to do minus the log. So if you're using my calculator, hit LN twice. Yes?
You get negative.
Do I what? Nope, I can't. I don't have X-ray vision.
So for this, for number 9, we just
Yep, yep, that's it. Okay, let's see. Who has not had a chance to come up? Paul, you get to do number 1. Aisha, can you do number 2? Joshua, do number 3. So you got to give me the pH for each of them, and we'll see how we did. It's on the left-hand side towards the top. It says LN, and you have to press it twice, though, to get log. Yep. Okay, as quickly as you get it done, let's put it up and show them how you did it. You'll take credit on that one. Yes? It's always 14 minus whatever you have to get what the new one is. One nice thing about having a tall and a short person up there at the same time, they can both write.
So for this one,
Or you could go this way minus the log and then take it away from 14 to get to pH. So whichever way you would like to go. I just know I always screw up this way because I forget to put the parentheses around the bottom. It is for me because this is about, yeah.
Okay. Can we go to two significant figures?
So whatever they gave you right here is what you get, but we always report pH to 2 after the decimal. Always, okay? Because that first number is not counted in significant figures, only after the decimal is significant. Okay? So it's sort of different with pH and pOH, but just remember, just remember that you need to use 2 after the decimal for pH. Oh, do not write E. Ooh, no. Ooh, growl. Times 10 to the negative 4. There we go. It's bad. If you actually use E or EE on different calculators, it'll give you a different answer. So that's why I frown on using E. Well, we'll check it with everybody. So. Okay, so you got an answer. This is your pH right here. Okay, so let's double check this. Everybody, number one, thumbs up or thumbs down? Got it? Okay, number 2, thumbs up or thumbs down? Number 3, thumbs up or thumbs down? Brandy, thumbs up or thumbs down? Okay, so we'll take this thumbs up and let you fix that. Okay, let's go forward. Here's another learning check. I want you to see if you can figure out everything. This is not necessarily on your thing here, just put it off to the side. But if you're given a pH of 8.3, tell me what the concentration of hydronium, hydroxide, and the pOH is. So find every corner on that chart. Given pH. Okay, so given pH, find me everything on the chart. The pOH, the OH concentration, and the H plus concentration.
So you just need to pick a way to do it all.
Yep. Or you can go down and get pH.
Technically, you could be able to go all the way around and get circumference.
Yep.
What one is it?
There, it's not there. Just put it off to the side. I just want to make sure we understand this. This will give you everything that you need to finish your home lab, your pH lab. If it was 1.995, yes. Okay, I'm going to give you one more minute to finish it up, and then we'll come back together. Welcome to my life, Ryan. Okay, 30 more seconds.
At first it's so scary and I didn't get it, but after using it a couple times I get it now. So.
Yeah, this is something that I would copy on my 3x5 card for this test. It's up to you though. Yeah, I love acid-base because it's all about what's going on in life. Okay? All right, here we go. Let's try the answers. How did you do? Of course, the concentration should have capital M by M. And I told you I like to go up and around, so I don't like to use the bottom equation because I always screw up. So if you use the bottom equation, you got the same answer, great. You did it right. Okay? I went up and around. So I went from pH down to concentration of hydrogen. I went from pH to pOH and then down to PO and down to concentration of hydroxide. So however you did it, if you got those answers, you're good. Okay. Know that pH of 8.5 is above 7, so it is a base. So we need to be able to recognize that. Be careful on the test because she will often put pOH and give you an 8.3 and ask you what is it an acid or base. Make sure you change it to pH before you decide. Yes? 8.3. Yes, this should be 3. Yes, I wasn't looking where you were looking, but yes, that should be 8.3. It's still a base. Yes?
Am I allowed to color code it, or am I not allowed to use color and it's just...
As far as I know, as long as it's handwritten, you just cannot print it. You can use colors. Some have used it. Yep. That's H+. Yep. H3O can also be written as H+, but she likes it H3O+. Okay, so the H+ is just a shortcut. So if you want to put that on your card so you know that H+ is H3O+, that's okay. All right, so going forward. Properties of acids. This is a general equation for an acid. Basically, it has to give off a hydrogen ion. Okay, and it's left with an anion that's negative that makes your salt. Yes?
Is that the dilution?
Nope, dilution equation is M1V1 equals M2V2. Yep, we've done that before. So it's right here. This is also a dilution equation we learned, which is C1V1 equals C2V2. C just meaning concentration. We're going to be using molarity, so it's M1. Okay. That's just a general equation for an acid.
That's what this is.
So we're just, no, that would be like saying this is H3O plus your concentration. Okay, you're okay. All right, so going forward, we need to be able to do this. This is what stuff we were just doing that I jumped ahead for. We're just going to go back and look at it. So remember I said MAVA equals MBVB? That just helps me so I remember base and acid, which one goes where. You can use 1s and 2s, but for acid base, it's a lot easier to do A's and B's because if I know my acid has a hydrogen and I keep that stuff together, and my base has a hydroxide and keep that stuff together, I won't screw up. So up here, here's my acid stuff, and we're actually just diluting it. So this is just an M1V1, sorry. That's okay, it doesn't matter. You can do the same thing. So we've got 750 milliliters times 0.500 molar divided by 6.00. And you plug it through. This is molarity. Molarities will cancel. And what do we get for an answer? Somebody's got a calculator because I can't. 62.5 milliliters. So how would you prepare that? So I need 62.5 milliliters of 6.00 molar. I'm going to take a volumetric flask that is 750. I'm going to add distilled water till it's about 3/4 full. So this is step 1. Step 2 would be I would add that. Step 3, I would swirl it. And step 4, I would fill till the bottom of the meniscus hits that line. Okay, so that's what we were doing when we were making our 0.1 molar sodium hydroxide. Except we didn't have a liquid, we had a solid we were adding. And we needed to have that space so that we could swirl this in here so we could get that dissolved. Okay? Number 3 is swirl it. That's just my shorthand version for swirl. Okay, you guys know that I'm very visual kind of person. If you haven't, you should by now. Okay, going forward. Oh, I've already just put that in there. Blah, 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 blah. Okay, Just as a reminder, how many remember the solubility tricks? NAG, SAG, right. So NAG was nitrates, acetates, and group 1 metals are soluble. SAG was sulfates, ammonium, and group 17 are soluble. Does anybody remember the exceptions? Castrobare, which is calcium, strontium, and barium, are not soluble with sulfates, and your heavy metals. So lead, mercury, and silver are not soluble with chlorides. Okay, so I will put this video up, so if you haven't remembered it, you could go back over and look at it. We're going to go ahead and go forward. So here I have hydrochloric acid. So we're going to write the molecular equation, HCl, and strontium, which has a +2 charge. That means I'm going to have 2 hydroxides. The molecular equation says OI, outsides and insides go together. So inside I've got strontium, which is a +2, chlorine is a -1, so I need 2 of them. Plus H and OH always make water. Balancing side to side, I'm going to have to put a 2 in front of the HCl and a 2 in front of the water. Everybody okay with that? So just balancing the equation. An ionic equation, I have to look and say, okay, this was AQ, this was AQ. Over here, this is a liquid. Water is always a liquid, not AQ. Strontium chloride, was that one of our exceptions to the rule? So what was not soluble with chlorines? Lead, mercury, and silver. So that's not one of our exceptions. So this is also going to be AQ. So anything that's AQ, I break up to its ions. So the ionic equation becomes 2H plus AQ plus 2Cl minus AQ yield plus strontium plus 2AQ plus 2OH minus AQ goes to strontium plus 2AQ plus 2 chlorine minus AQ plus 2H2O liquid. So if it's a solid or a liquid, I do not split it, or a gas. Okay, to get my net ionic equation, anything that's the same on both sides, I can get rid of. So as I'm looking at it, chlorine is the same on both sides, right? Exactly the same. Strontium is exactly the same on both sides. Is there anything else that is the same on both sides? There shouldn't be. There's nothing exactly the same on both sides. So we come down to our net ionic equation. I would write 2H plus AQ plus 2OH minus AQ gives me 2H2O liquid. But looking at that, I can't have a 2 in front of all of them, right, Ryan? So I'm going to get rid of the 2 in front of all of them. I'm just going to write H plus AQ plus OH minus AQ gives me H2O liquid. Because it's in front of every single one of them, so it will cancel out. It's like putting an equation in math and you have a 2 in front of everything on both sides of the equal sign. Yes. Okay, so that's a net ionic equation. Just remember your solubility rules. What I like to do is say, okay, aqueous, 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 they're all going to split up. I do a shortcut. And I say, here's what I'm trying to make. What ions make that up? Well, H plus and OH minus. Okay, does that make sense? So I shortcut this. But these ones that are underlined, these are known as spectator ions. Meaning that's what they do. They just spectate. They don't really do anything. They're just staying as ions from one side to the other. Okay, so if she asks you for the spectator ions, that's the thing that doesn't make the solid or the liquid or the gas. Okay? So let's do calcium and cold water. So, reaction, calcium, Ca, solid, right? Calcium, solid, plus water will give me what? So you got to remember that water is what? Made up of H and OH, right? So what part of the H and the OH will calcium go with? The OH, because calcium's a positive. So I have a +2 with calcium, and it'll go with the OH, so I need 2 OHs for it to go with. Plus, what got left out? H. And H is one of our bronchial, so it's going to become H2 gas, right? Okay, the only one I don't know is calcium hydroxide. Well, calcium hydroxide is one of our strong bases, so it's going to be aqueous. It's going to be dissolved in water because it likes to split up. Well, the ionic equation for this is very simple because most things don't split up. What is the only thing that splits up? The calcium hydroxide. So I just rewrite it. Calcium's H2O as a liquid goes to Ca plus 2 AQ plus 2 OH minus AQ plus H2 gas. Okay, is there anything that can be cut out? The exact same on both sides. Is calcium the exact same on both sides? No, one's solid and one's aqueous. One has a charge, one doesn't. So guess what? On this one, my net ionic equation is the same as my ionic equation because I can't cut anything out. Okay, going forward. So describe how you would prepare. This is like what we did in the back last time, except this time you have a stock solution instead of weighing out some sodium hydroxide. So to do that, we would just use M1V1 equals M2V2, or C1V1 equals C2V2. So plugging in, we are trying to find out how much volume of the stock we need. So I'm just going to go V2 is equal to M1V1 divided by M2. Plugging in 200 milliliters times 0.1 molar divided by 5.7 molar. Molars cancel. We find out how much we need to put in. How much? 3.5 milliliters. So I'm going to take my volumetric flask that goes to 200. I'm going to fill it with distilled water. Second, I'm going to put that much of the NaOH, that is 5.7 molar in, that's number 2. Swirl and then fill to line. Okay, so I make it. Okay, let's do this next one. Nitric acid and calcium oxide. So nitric acid is HNO3. It's one of our strong acids. It's going to be AQ. Plus calcium oxide. What's calcium oxide? CaO. And this is chalk. The calcium oxide is chalk. So it's going to be a solid. And OI, outsides and insides go together. So what are we going to make? Insides make what? Ca parentheses NO3 parentheses 2. And it's a nitrate. By my solubility rules, they're always soluble. Plus H and O, which make water, which is a liquid. Okay, so looking at this, is it balanced? The answer should be no. So we put a 2 here, and that should balance it, right? Okay, so writing the ionic equation. This is going to split 2H plus AQ plus 2NO3 minus AQ plus CaO solid yields Ca plus 2 AQ plus 2NO3 minus AQ plus H2O liquid. What's the same on both sides? What's the same on both sides? We're just going to finish this one. The nitrates should be the same on both sides. We're going to get rid of them. So our net ionic equation is just 2H plus AQ plus CaO solid yields Ca plus 2AQ plus H2O liquid.
So how do you not split up the water and
Water you'll never split. It'll always be liquid. It's not AQ. You can only split AQs.
Never split up liquids or solids.
Liquid, solids, or gases have to stay. Okay, so now we did not get as far as I wanted to. So what we're going to do is we're going to have 3 labs due next Thursday, but we're still going to do the buffer lab next Thursday because I can't do it when I'm not here. Okay, so we're going to do that lab next Thursday while I'm here, and then I will record lectures for you so you can finish that lab with a buffer. Okay? No, we're not going to have the buffer lab be part of that notebook. So you can put it into your lab notebook, but I'm going to only grade the 3. The home lab, pH lab, the titration lab, and the beverage lab. Okay?